Okay. A normal distribution applies the data that when you look at the distribution, right, the histogram, the bar chart, whatever you want to call it, it looks like it's unimodal. It's got a peak in the middle, and it's symmetric to both sides. That it doesn't have to be perfect. I mean, data is almost never perfect. Just like when we make the best fit line through a scatter plot, the reason it's called best fit is because it's not a perfect fit. It's just the best fit that we've got. Well, this is the same thing. When we call something normal, it doesn't necessarily mean it's perfectly normal, but it's approximately normal because it's unimodal and symmetric. Now, examples of the kind of processes that lead to normal distributions are, for example, they're usually the result of random processes. Right? What does random mean? Yeah, it's kind of, you know what the possible values are, but you don't know what your value is going to be for any particular roll of the dice, let's say. I mean, if you walk from your last class to this class, does it take you exactly the same amount of time every day? No. And how many different things can affect how fast you get here? You stopped to talk to friends. You had to go to the bathroom that day. The hallways were crowded. So, which things happen on any particular day is somewhat random, which is going to make your time that you arrive random also. Now, if you added up, let's say Ryan's times for a month, right? It would have a mean, right? There would be a mean. And if we did a bar chart, the biggest bar would probably be in the middle with the mean. And then there would be less as you go to the sides, away from the mean to the right or away from the mean to the left. We would expect that the graph kind of falls away because it's a result of a random process. I mean, height's another thing that can be random because what's random about your height? Yeah, genetics. If you control for age, then what nutrition you've had. I mean, all these things can affect it. Yeah, well, you probably wouldn't want to put both males and females on the same graph because it would likely be bimodal if you did. There would be one for the boys and one for the girls. Generally, anytime you do measurements are fraught with error. And error doesn't necessarily mean wrong, but take, for example, if I asked everybody in this class, which is 20 right now, to take a ruler, a 12-inch ruler, and then try to measure the distance from that side of the trailer to that side of the trailer. Do you think that we would all come up with exactly the same measurement to 1/16 of an inch? No. But if we graphed them, right, if we did a bar chart or a dot plot or a histogram with it, what you'd probably see is a big bar in the middle, which is the mean, and then some that were more than the mean and some that were less than the mean, but probably the most accurate would be probably the one in the middle is probably the most accurate. The guy who first came up with this stuff was a mathematician named Gauss, and he was in Germany in charge of, land measurements, acreage, distances between cities and that, and he'd send his team out to do the measurements, and they'd come back with different values all the time. And it wasn't far off, but it wasn't exact. And it really made him think about, the kind of errors that you get. And he noticed that if he did this kind of bar chart or histogram or whatever, that it always peaked in the middle and it fell away to the sides. That is ultimately the origin of normal distribution.